Our last topics for this chapter is hysteresis. This is not a state of being hysterical. It's a property of magnetic materials, and it really deals with how well they hold their magnetic properties. So we look at a material that is just random. This would be non-magnetized. So under a microscope, you look at iron or other magnetic materials. There's like these grains inside, and these grains will have an individual magnetic field for each one. And in a non-magnetized material, these magnetic field lines are pointing in all sorts of directions, and it ends up canceling out the magnetic field. Now, if you put a magnet inside of a magnetic field long enough, it will magnetize it. And that's because all of the magnetic fields in all the little pieces start to align themselves in one direction. But once you get all of these magnetic fields for the little pieces or grains inside of material aligned, it doesn't matter how much more magnetic field you put it in, it's not going to align any tighter. Once they're there, they're there. So because of this, we get this hysteresis. And the way we describe hysteresis is with a hysteresis curve. All sorts of different materials have their own curve. And what it's saying here is if I have a non-magnetized material and I put it into a magnetic field, its magnetic properties are going to increase until it gets to a maximum. Can't go anymore. And now, as I decrease the magnetic field that the material is in, and I end up shutting it off, there's no magnetic field that's influencing the magnetic material, there is a residual magnetic field from the material that remains. That's because all of those magnetic field lines are lined up in the same direction. So it's going to take a certain amount of magnetic field strength in the opposite direction to get rid of the residual in the material. So there's a certain point that the magnetic field in the opposite direction will cancel out the magnetic field that was created in the material. And then as I increase that magnetic field in the opposite direction, I'm going to eventually peak out the magnetic field in the magnet. It has flipped all of these magnetic fields. So in one direction, when I was at the top, at B, all of these were in this direction. And now, when I'm at E, I have flipped all these magnetic field vectors. They're all flipped and pointing in the opposite direction. And now I have the same thing happen. I decrease my magnetic field, and I'm going to get a residual magnetic field. This time it's going to be in the opposite direction. And if I want to get rid of that, then I have to increase my magnetic field, and it will drop the magnetic field inside the material down to 0, and then I can do the same thing and magnetize it again however I want. Now, these are very useful. Speakers will have usually a hysteresis chart, at least the good ones, will have a hysteresis chart, and the hysteresis charts are going to be fairly thin for those. You want it to be pretty thin, like so, because then you're not wasting a lot of energy to get this magnetic field back to 0. If it's a fat one, then it's going to require a lot more energy to get rid of these residuals. And your speaker won't respond very quickly, which means it'll be muffled, it'll sound bad. So these hysteresis curves are important when you're wanting to evaluate a magnet and understand how fast things are going to respond based on the magnetic field inside of that magnet and how that magnetic field changes.